Hello my dear students, I am B S Pandey. Today we are in lecture number 65 of standard 12 and we will continue the chapter Electromagnetic Induction in CRT chapter number 6. Okay my dear students, so we are in lecture number 65. It is the chapter number 6 of NCRT Electromagnetic Induction. So my dear students, in last lecture we have studied about the magnetic flux and we have done some topic regarding the quantities of magnetic flux. Okay, today basically we will study the induced quantity and then we will study the Lenz law. Okay student, so the first we are going to study today, it is induced quantity. Induced quantity due to change in flux, magnetic flux. Alright, so the first quantity my dear students will study, it is, let me recall the induced EMF as well. Suppose this is magnetic field, uniform magnetic field which is in the direction of x-axis. A coil this is the coil which is placed, and if this magnetic field changes, then how the quantity we can deal here. Suppose here the you can say the cross-sectional area of the coil, it is A, number of turns, alright, number of turns. So we are going to consider here the quantities that are associated with this change in flux. Okay, this is very important my dear students. So the E induced, that is the induced EMF, let the resistance of this n turns of the coil, it is R. It is the resistance of coil. Okay, now we know that according to Faraday law that we have studied, E induced, it is minus n d phi by dt. Alright, here phi is nothing but the B dot A, or we can write BA cos theta. My dear students, if this coil is in a static state, not moving, only the magnetic field is changing, so that the flux changing. Remember, to change the flux, we can change the area, we can change the magnetic field, or you can change the orientation of the coil, that it can rotate. So here we are changing the magnetic field, that is the field is changing, fluctuating. Alright, theta it is, if theta is 90 degree, then my dear students, we can write the flux, it is as B A, sorry, it is 0 degree. At 0 degree, then B times A. Now E induced will be minus n d BA over dt, and here we can write the minus n if cross-sectional area is constant and the field is changing, that is B changing, then it is dB by dt. This is the E induced. Okay my dear students, now remember this dV by dt, the rate change of field. Which field? Magnetic field. And the SI unit, it will be the Tesla per second, if it will be given in the question. So in this way you can find out one quantity due to change in flux. Of course, if magnetic field is changing, the flux will change. Now, my dear students, the next quantity we will study, and this next quantity will be the current that we have studied already. Okay. Now, we know that E is equals to IR. If it is the induced EMF, then this is the induced current. Due to this resistance, this current induced in the coil. Okay, my dear students. Now, we can write here I induced, it is E induced over R. Alright. And this I induced, my dear students, directly we can write this E induced we are having here, the induced minus NA dV by dt, or in terms of, or in form of this flux, my dear students, you can write this E induced can be minus N d phi by dt, minus N d phi by dt. Yes, could you write? Yes, d phi by dt divided by R, that is R. We can write this one, or we can put this value, alright, to find the I induced. Okay, now let me study the next quantity. It is induced charge. Induced charge. You can write, my dear students, induced charge. What will happen to the induced charge here? As you know that I is dq by dt. Am I right? Yes. So this dq can be written as I dt, of course, which type of I? It is induced current, times dt, and we know that I induced, it is N by R d phi by dt. So this can be written as thus I, the magnitude, you can say the I magnitude or change in flux here. If d phi by dt is the phi final minus phi initial, then this negative sign will change phi initial minus phi final. You should be conceptually sound, my dear students. Never just get confused with this negative sign. Okay, you can change this equation. Now, I induced can be written as N by R. I induced we are writing d phi by dt times this dt, and this will be dt cancel out, so N by R d phi. Okay, this is the dq, that is the charge induced, N by R, and d phi, my dear students, what we can write, this d phi, the phi initial minus phi final. Mathematically this is the final minus initial, but we know that this negative sign becomes the minus I phi initial minus phi final, and this is the induced charge, that is the change in flux. If you are having the change in flux and the resistance of the coil, directly you can get the charge induced in the coil, my dear students. From here you can find out the various quantity that is inducing in the coil, my dear students. The electric field also we can study, that is the induced electric field. Alright, so the number of physical quantity we can study here. Okay, my dear students. Alright, now we'll move to the next segment. It is, suppose here the magnetic field was changing. Alright, what will happen if this magnetic field is not changing? Actually, to change the magnetic flux, if the coil orientation changes continuously. Try to recall, in standard 10 you have been studied about the generator. Okay, what was the generator? Actually, you have been studied the AC and DC generator. My dear students, the generator, it was when this coil, armature coil, rotates in between two magnets, then flux changes continuously, and EMF and current induces. Alright, so the same thing we are going to study here. Try to understand. Suppose if a coil is placed, you can write here the induced EMF and current due to rotation of coil. This is the very important rotation of coil. Suppose this is a coil and it has been placed in uniform magnetic field. Remember, now this B is not going to be changed. Uniform magnetic field. Alright. Now, if this coil is rotating about this axis, alright, one of the diameter, vertical diameter, and the coil is rotating with the speed omega. Alright. For one time, we study this cross-section area in this direction. Okay. We give some time t. Alright. In this t second, the coil rotated by a certain angle. Suppose it is theta. That is, the twisting is theta. Alright. And the coil rotated by theta. This theta is the angular displacement in t second. Alright. It is in t second. Now, if rotated in t second, then this theta can be written as omega into t. Am I right? Yes, this can be written as theta equals to omega into t. Now, to find EMF induced, we should have the flux. Alright. So, right here, the flux. It is B dot A. We know that since this coil is rotating and angle is not constant, so angle will change regularly. So, we are having here the phi equals to BA cos theta. Alright? Yes, genius. Here. Now, we know that according to Faraday law, E induced, let me know in comment section, my dear students. If I am going very fast, then I can slow down myself. E induced, it is BA cos theta. So, it will be the BA minus d phi by dt. Alright, and for n turns, this can be written as the minus n d phi by dt for n turns of the coil. We can write minus n d phi by dt. Okay, minus n d phi. What is phi? It is BA cos theta. Alright, over dt. My dear students, we can write minus n. Here the constant, as you know that B is constant. I told you, na, B is constant. Area is also not changing, my dear students. So BA cos, here the D cos and theta can be written as the omega t over dt. So this E induced will be how much? Minus n B A, and cos omega t will be differentiate with respect to the time. It will be minus sin omega t into t. Alright, yes. Sorry, omega. No. It's omega. So it is NBA omega sin omega t. This minus plus I think. Yes. And this value, it is called the instantaneous value. Why? Because we know that as this coil will rotate with the time, the theta will change regularly and this value will change. And this value will change from where to where? Minus 1 to plus 1. It means its peak value will be with plus 1 and it is its peak value with plus 1 and it is peak value. Suppose we are representing the peak value by E naught. It is the peak value. That is the maximum. So this ET can be written as, this is nothing but the peak value, E naught into sine omega t. My dear students, we will start the next chapter, that is AC, from this equation only. So bear in mind this equation. Alright? Yes. Now, there are a number of questions in NCERT. It is given, I think the first or second question you will find in NCERT on the basis of this formula, and you should have the concept how to derive this formulas, my dear students. Okay, and these are the not very difficult, my dear students, that you are feeling very difficulty while solving this type of question. These are the very easy one. Okay, my dear students. Yes, now let me move towards the Lenz law. All right, Lenz law. Actually, while the lecture was going on, the last lecture, I have just discussed 2 or 3 times about the Lenz law. You know, you remember na, that this E induced minus n d phi by dt, this minus sign actually shows the direction of EMF, and it is opposite to the change in flux, and it was well defined by and well explained by Mr. Lenz. That's why we are going to study here the Lenz law. Okay, my dear student. So give the heading Lenz law. Actually, Lenz law, it is, remember, based on the conservation of energy, basically. Yes, it is based on that conservation. Here, let me write. Lenz law. Why and what this law will give you here in this chapter? So this will give you the direction of E induced and I induced. Remember, gives direction of E induced and I induced, okay, due to change in magnetic flux. All right, my dear students. Okay, now try to understand. Actually, you can write the statement of this law. I am telling you, and the statement is: an EMF induced in a coil due to change in magnetic flux linked with the coil, an EMF induced in a coil due to change in magnetic flux linked with the coil in such a way it opposes, which one? Actually, EMF induced. Okay, it opposes the cause. It opposes the cause that has been induced it. Actually, the EMF opposes the cause that has been induced that EMF. You can say, if it is the son, it is against his father. All right. Yes. Now, try to understand. And how this will oppose, you have to study, and that will make certain question. So, try to understand here. Suppose this is a coil. As we know, if this is the north pole and you will bring a north pole, what will happen? If you bring this north pole, of course, it will repel this north pole, and this pole will not accept this north pole coming towards that north pole. Okay, my dear student. Now, try to understand. Here, this is a coil. You can see the face of this coil from here. You are the observer and you can see this face. Alright. Now this is a magnet, north pole. This is the coil of turning. Suppose the number of turn, it is only 1. And we also know that this is magnet. So of course it has some field lines. Alright. As we move this magnet towards the coil, what will happen? Due to motion of this magnet towards the coil, there will be change in flux in this coil. Of course, there will be change in flux in this coil, and this coil will experience change in flux and EMF will induce in this coil. Now, the EMF is inducing, due to that EMF, a current is inducing in this coil in such a way that it will start opposing this magnet. Alright, we know that if this is a current carrying coil, alright, if current is moving, then we know that this will be considered as the south pole, and if the current is moving in this direction, this will be considered the north pole. We have studied already in second last chapter. Okay. Now, due to change in magnetic flux, there will be current in this coil due to change in magnetic flux, because this magnet is moving towards the coil. Due to change in magnetic flux in this coil, there will be EMF induced in this coil, no doubt. And due to that induced EMF, there will be current induced in this coil. And due to current, we know that a current carrying coil behaves like a short bar magnet. Now, if this magnet is moving towards the coil, then which pole this coil will induce to oppose this magnet? Answer is, if north pole is coming towards the coil, then it should be pair north pole. Yes, to oppose, because this coil do not give the liberty to come this magnet towards itself, and a north pole will be pair. If north pole pair, my dear students, you can say the current will be in direction. So this is the Lenz law. According to Lenz, we got the direction of current. Now it is very easy. You can say if a north pole is coming towards the coil, then the current will induce in this direction. This is very easy to explain in which direction. Now, let me give you some example and try to find out the direction of induced EMF. Remember, this is the induced, I induce. You can write I induce, okay, or E induce. You can also apply a battery. Suppose you have to connect a battery to show the direction of current. It's very easy. You will apply here the positive terminal and here negative terminal. The positive and negative. Why? Because current also should be moved from positive to negative. Suppose in question, if it is asking to connect a capacitor, okay, to connect a capacitor to show the direction of current, then you should apply the plates of capacitor. But remember one thing, the polarity of capacitor will be just opposite to the battery, because we know that the battery supply the charge, but this capacitor accept the charge. If it is positive, then in capacitor this will be the negative and this will be the positive. All right, my dear students. So if you are asked to apply here the battery or connect the battery, you can connect the battery. If you want to connect a capacitor, you can connect the capacitor. All right. Yes. Okay. Now let me give you some example and you will try to solve these examples. Here. This is a coil. You can see from above this coil, and this is a magnet. This is example. You have to think. Meanwhile, I am drawing the coil, and then after I will give the answer. This is the south pole. It is coming towards the coil. This is the first example. Second one. This is the north pole, it is going away. The plane of the coil you look from above. Here, the two example. One more example. Third one. you have to find the direction of induced EMF or current in each three coil. You can write clockwise or anti-clockwise also. Okay, my dear students. So try to think the answer of this one. Let me draw this one. I hope you got the answer of this question. Now let me solve. Yes, the south pole, it is coming towards the coil. Of course, to oppose the south pole, it will appear a south pole into it. So the current will flow in this direction. Alright, and this is clockwise from above. If the observer, it is the beautiful observer, then current will be clockwise. Alright, yes. Now here, if observer is here, this is the observer. If observer is here, for this observer, the direction of current will be the north pole, it is coming away. Then to oppose this north pole, this will induce an electric current, so that it do not want that this north pole go away. So it will start attracting. Okay, this is very mad. That coil, don't let that magnet go, and don't let that magnet come towards it. So the north pole is going away, it will appear a south pole again, and the current will be again in clockwise direction. Now you can find the answer of this one by yourself. Okay, my dear students, try to find out answer of this question by yourself, my dear students. I hope that you have been solved. Okay, one more question. Let me give you the homework. This is your homework. Here, this is a coil. This space is empty. A magnet is freely fall. Suppose the north pole magnet with an acceleration a. Now the answer, the options I am giving you. The first option, this a should be less than g. Second option, this a should be greater than g. Third option, this a will be equals to g. And the fourth option, a will decrease above the coil and increase below the coil. Alright, so there's four options. You have to find which one is the correct option. And also, my dear students, you don't have to tick only the option, yes, this is the correct one, but also you have to tell me why this one is the correct option. Okay, I hope that you can find out the reason. Remember, this is freely falling and this is a ring, metallic ring, in which an EMF can be induced. You have to find which one is the correct option. Okay, now my dear students, the induced EMF, we have studied the 2 or 3 way. One more way to inducing EMF. So give the heading, inducing EMF due to motion of coil. Alright. Remember, I'm not going to deal here the motional EMF, my dear students, but only using Lenz law we are going to find the polarity of induced EMF. First we will discuss the polarity and then we will discuss the magnitude of induced EMF by the motional EMF. So here, suppose this is a very important. Give here attention, my dear student. Here one coil, it is the coil moving inside the magnetic field. This is the magnetic field, and I know that you can understand the magnetic field. It is moving inward and the dot gives the representation of outward. So this this coil is moving inside the magnetic field. My dear students, you have to find the direction of current, whether it will be the clockwise or anti-clockwise. Okay, so how we will discuss, look at it. As this coil, let me draw this coil a little bit of laser. As this coil will start moving inside the field, suppose if it is out of the field, what is the net flux outside the field? It is 0. No field lines trapped by this coil. As it will start moving inside the magnetic field, the flux will increase or decrease? Answer is yes, it will increase, no doubt. It will start increasing the magnetic flux. Alright. Now, if flux is increasing, then it is very important to understand, suppose if this is the coil and flux is increasing, then our aim to find why this flux is increasing. Due to coming of north pole or south pole, because if north pole will come, then flux will increase. If south pole will come, then flux will increase. But in both the case, there will be change in direction of induced EMF. If north pole is coming, then it becomes north. If south pole is coming, this becomes south. But in both cases, EMF will induce. So here our aim is to find the polarity due to which pole the flux is increasing. Okay. So you are the observer and you are looking the magnetic field lines, and here the cross magnetic field lines. What does it mean? Suppose a magnet you are having in your hand out of this board. Okay. You have to suppose in this way. Then only you can solve this type of question. You are having a magnet. Of course, if the field lines is going into the board, then which type of pole this will be? Of course, it is north pole, because north pole leaves the magnetic field lines to move into the board. If field lines is coming, it means this is which type of pole? It is south pole. Exactly. Here the magnetic field lines going into the board, it means we are having north pole. Now, if this coil is moving inside the field, flux is increasing. And if you are having the north pole, what does it mean? The north pole going towards the coil, that's why the flux is increasing. If you're having a coil, you will move this magnet towards the coil, the flux will increase. And here the flux is increasing. As this coil is moving inside the field, flux is increasing. It means this magnet, which pole this was? Yes, north pole. And this is the coil. It means you have to suppose this north pole is going towards the coil. If it is moving inward, it means north pole is going towards the coil. If north pole is going towards the coil, which pole it will appear? Of course, north pole, because north pole is coming towards the coil, and it will start opposing by appearing a north pole. It becomes north pole. Okay, you can repeat my lecture to understand it again and again. I will give you one more example. Okay, not more than that. So the answer is anti-clockwise will be induced. Okay, look at here another example. Suppose a coil, it is inside the field and it is moving out. All right, it is moving out. Then which pole will be induced? What will be the direction of induced EMF if it will be out of the field? And what more question, my dear students, what will be the induced EMF if it move inside the magnetic field? if it move inside the magnetic field. Remember, inside the magnetic field, if the field is uniform, then inside the magnetic field there will be no change in flux. The maximum flux, it has been trapped, it is not changing inside the magnetic field. Alright, so there will be no induced EMF. You will write the 0. There will be no direction. As it will move inside the field, the flux will increase. As it will move outside the field, flux will decrease, and in both cases the EMF will induce. But inside the field, it is moving inside the field, there will be no change in flux and no EMF will be induced. Okay, now here, this coil is moving out of the field. Which pole this was? If it is a magnetic field inside the board, of course we are having north pole. And if flux is decreasing or increasing, exactly it is decreasing. It means we are keeping this north pole away from the coil. If north pole is going away from the coil, it means it will appear a south pole. Yes, it will appear a south pole. Now this will be the direction of, here I told the direction, I think anti-clockwise, no? Yes, this will be the clockwise direction. Be sure. Okay, this is the clockwise direction. Now on the velocity, it will depend what will be the magnitude. If you are getting this coil slowly, the induced EMF, magnitude of induced EMF will be small. Otherwise, if you keep it very strongly, then the induced EMF will be so high. Okay, so this was the one way to find the direction of induced EMF. My dear students, next day I will discuss, that is in next lecture I will discuss for a few more way to find the direction of induced EMF in a